All right, so just walking us through the study guide. So number here, obviously climate, it's over a long period of time. Number 2 should be weather. It's over a short period of time in a very localized area. So what are the 2 factors that control weather, climate? The 2 largest ones are going to be temperature and precipitation. Now number 4, you guys constructed a graph called a climatograph in your presentation that shows both of these. So it's supposed to say this is created in part. I'm talking about climate. So climate is created in part due to the unequal heating of the Earth, which is a result of solar radiation. Now at some areas, the sun's energy is more, you could use concentrated, direct. That would work fine here. At the poles, you could use, it's dispersed, it's more spread out, it's weaker. It's just the understanding that at the poles, it looks more like an oval, and at the equator, it looks more like a circle. So this is just illustrating it, again, just more direct right at the equator, again, more spread out over at the poles. Over here, number 8, we're looking at the albedo, and then just different examples here. So an example of something light in color is going to reflect more solar radiation, like ice, snow. Examples of things that absorb or reflect less solar radiation, concrete, dirt, and this is just showing how most of that energy is reflected back out into space by light colored objects, and less of it is reflected by dark colored objects. More of that is absorbed. Back over here at number 11, Earth has a tilt of 23.5 degrees, and this is going to lead to the seasons. Now this isn't on the study guide, but again, most people understood this. If it's tilting away from the sun, this area it's going to be summer and this area it's going to be winter because it's tilted away, it's farther away, less solar radiation, gets colder. But as we circle in 365 days a year, in 6 months we're on the other side where we're tilted towards the sun, then we're going to have summer and this area is going to have winter. So moving on to number 12, the Earth has 5 layers. So if we're looking over here, here are 5 layers. I'm not expecting you to know, how thick each layer is. Just know that the troposphere is relatively thin. Now we live in the troposphere, which is this bottom level. And this is also where most of the weather occurs, down in the troposphere. Now blank is below the mesosphere, so if I come back over here, that would be the stratosphere. Now the important thing about the stratosphere is that it contains the ozone layer. Now is there ozone in the troposphere? Yes, but it's a bad thing when it's in the troposphere. It needs to be in the stratosphere to protect us from ultraviolet light. So this right here is, again, ozone, which protects us from UV rays. For 21, here we have currents as a continuous movement of ocean waters. And they form these gigantic patterns called gyres. So just make sure you know North Pacific, South Pacific, North Atlantic, South Atlantic, Indian Ocean, and all the currents that go along in there. So make sure you review your currents too, because I'm probably going to ask you about that as well. Now, what shapes these gyres? Well, what shapes them is a combination of the wind pattern, because it's pushing it this way or this way with the westerlies, and continents, because the trade winds push it this way, but then eventually it hits land. So it has to move up, it follows the coast, and then when there's no land in front of it, the westerlies come along. Once it hits land over here, goes down. When there's nothing in its way, the trade winds pick it up, and it has a circular pattern. Same thing, trade winds are coming here, pushes it till it hits South America, moves down. When nothing's in its way, the westerlies pick it up, hits Africa, scoots back up, and has this rotation here. So for 18, 19, and 20, just make sure you know which currents these belong to. There's actually one more set that you're going to need to know. For 22, we call the rising of cold water from deeper layers up to the top upwelling. And here's a good example of that. Again, you have surface winds like the trade winds, for example. This ties back to El Nino, pushing warm water away, so it creates an empty space where cold water is brought up to the surface. This is why off the coast of Peru you have this pool of cool water here, and the warm water is being pushed towards Australia. All right, so here this one's a little bit difficult to explain like visually. Look up a YouTube video on it. It's probably the best bet. You can go to Apes Lessons or tiny.cc/Apes Lessons and find one. So this one's called thermohaline circulation, and really it's caused by a difference in density that has to do with temperature and salinity. basically the amount of salt that it has. So over at the poles, you have very salty water, you have cold water. It's very dense water that is going to sink. So that's dense water. So and this ends up mixing cold water with warm water. You could even say it's mixing high salinity and low salinity. But the best way to look at it is like this. So you have water that's warmed at the equators and it moves towards the poles, and then eventually it cools down and it sinks underneath it. Now the hard part here is this is not like sea surface temperature. This is not like currents. This is happening in 2 dimensions. This is happening at the surface and underneath. So I'm going to show you this other one. Don't get this confused with upwelling. So just imagine this is the equator. So we're looking at the planet sideways. So water is warmed at the equator. It kind of floats towards the poles. So kind of like right here, warms up, floats towards the poles. Once it gets to the poles, it starts to cool down and become more dense. And it will sink underneath the warm water, which is kind of what's happening here. It kind of cools down and sinks underneath the warm water and will travel on the bottom of the ocean until at some point it reaches the equator again, warms up, and then does the cycle all over again. All right, over here we're talking about oceans. So phytoplankton are microscopic free-floating photosynthetic organisms. Here are just different layers of the ocean. The 2 most important here are the epipelagic. This is where there is light enough for photosynthesis to occur. This is called the mesopelagic, where there is light but not enough for photosynthesis to occur. And then this is called the bathypelagic. This one is an area where no light reaches, no photosynthesis occurs. Down over here, these are all unquisite, so they have to do with coral and coral bleaching. Kind of running over here, I'm trying to leave some time over here so it doesn't extend past 15 minutes. These are all areas of lakes that you can look inside of your notebook. Just make sure you're familiar with 44 through 47. All right, now kind of getting us to the big stuff. 39, which is related to this one over here, is an El Niño event that will occur every 2 to 7 years. Down over here, NOAA, so National Oceanic Atmospheric Administration, just the acronym is fine, monitors something called the TAO, T-A-O, TAO buoy array. Now, we look at sea surface temperature off the coast of South America, Peru, and if it's over 24 degrees, then it will be an El Niño year. What about depth data? So you're looking at depth data, and if the 14-degree line is between 0 and 200, it will not be an El Niño year, meaning that it will be a normal year. So I would go to that tiny.cc/SCAPES just to refresh how to read these 2 charts. Now, in order to be considered an El Niño year, you only need one of these charts to indicate it. So if the SST says yes, but this says no, it's going to be an El Niño year, but probably a weak El Niño year. So if both say it's going to be an El Niño year, it's going to be a strong El Niño year. If this says normal year, this says normal year, no El Niño will occur. All right, so during this event, the trade winds are either going to reverse or weaken. If they weaken, it's probably going to be a light El Niño year. If they reverse, if they flip around the other year, or the other way, it's going to be a very strong El Niño year. And this is causing warm water to move eastward. This could be towards Peru, towards Africa, towards Europe, towards North America. So before I show you how it moves, again, just a kind of a quick recap. Peru's over here. You have Australia over here. You have trade winds pushing warm water away from Peru. That's why warm water is building up here. It evaporates up here, rains down on Australia's side, keeping Peru relatively dry. So that's why that warm pool is always over here with 24-degree or lower water off the coast of Peru. Also, when you're looking at the sideways depth chart, you have this curve, that 14-degree line. So here's 0, 200, maybe somewhere around over here. You just need to make sure, does that 14-degree line lie between 0 and 200? Now, if it's way down over here, like 250, 300, it didn't make it to 200, between 0 and 200, then it's going to be an El Niño year. So that, I'm looking over here at an El Niño here, where though trade winds are weak, it's not pushing all that warm water away. It causes rain to come closer to Peru, makes Australia drier than it normally is. And you notice here that line that was curving up is now lower or underneath 200. Again, imagine 0's here, 200's here. It's not making it up to 200. So we would consider this an El Nino year. But this is happening everywhere. Again, you have warm water being pushed this way on your south equatorial current, okay, pushing this way. But the same thing is happening here. Again, warm water is being pushed this way normally, but during an El Nino year, it's going to move towards North America. Again, warm water is being pushed normally towards this side of the U.S. and this side of South America. Again, if they weaken, it's going to move towards Australia. It'll move towards Europe. Okay, so wind patterns caused by two things: the unequal heating of the Earth and the Coriolis effect. We have three major wind patterns: polar easterlies, westerlies. For this unit, trade winds are going to be important. So these are located between 0 and 30 south and 0 and 30 north. This will be important for one of the questions for the El Nino part. So going back to this part, the Coriolis is just that change or curve in an object's path due to the Earth's rotation. That's that weird, like we watched a video where they were on this weird spinning thing, they threw the ball, and the ball moves straight, it just looks like it's curving. And going back to this last one, again, the trade winds is what's going to determine whether or not an El Nino will occur. So coming over here and looking at a few of these questions, what causes an El Nino year? This could be two separate answers. One, like if I ask if it's man-made or natural, obviously it's natural. We have nothing to do with it. It just occurs. But what causes it in terms of like, okay, if we can point to something, it's the weakening of the trade winds or the reversal of the trade winds. Frequency, 2 to 7 years. What agency? That's NOAA. Specifically, how does this impact global weather or climate? Cite specific examples. Basically, it causes your normal climate to reverse or change. So Peru is normally dry, becomes wet. Australia, normally wet, becomes dry. But the same thing is true of some of these other areas. So like right here, Australia is normally wet. Well, guess what? This side, Asia, gets normally wet. But during an El Nino year, all this warm water that's normally on this side moves this way. And so areas that are dry like California, Peru, we get all of that rain. So we're normally dry, but it becomes wet. Over here, again, warm water is being pushed towards this side and this side. So normally this side of South America is wet, this side of North America is wet. During an El Nino year, that warm water moves this way. That means Europe gets more rain and Africa gets more rain. All right. All of these change global, like weather and climate. What layer is it happening in? That's happening in the troposphere. Again, natural man-made, we covered it. SST data. Just make sure you can read an SST chart. Depth data, make sure you can read a depth chart. Really for SST, what you're looking at is the water off the coast of Peru or near the equator 24 degrees or under? Depth data, that 14-degree line, is it between 0 and 200? That's what you're looking at. So if I'm looking here at 1997 on the sea surface temperature, looking right around the equator, so like right around here, do I see 24 degrees? Again, you want to count backwards just to make sure. Usually they're going by 0.5s, but again, you just want to make sure. Obviously this one is, even if it was going by ones, you're not going to reach 24. So according to this is going to be an El Nino year. All right, what about the depth data on this one? Again, I'm following that 14-degree line, and it stops right here. Now, normally I drop a ruler or a piece of paper right across here to see where my 200 goes. So these go by 50, so that's 0, 50, 100, 150, 200. So if that 14-degree line is between, if that 14-degree line reaches between 200 and 0, basically in this area right here, it's a normal year. But look at the 14-degree line. It's way under 200. Okay, so again, that's 150. Our 200 is over here. Again, way under 200. This indicates it's going to be an El Nino year because the sea surface temperature and depth data said El Nino years. This is going to 1997 was a very strong El Nino year. All right, remember we already talked about whether we need one or both. We can skip the latitude range. What are the causes, or what is or are the causes of movement of wind in this area? SST chart. trade winds. Okay, so trade winds are the cause of moving that warm water from one side to the other. Since water is being moved, be able to identify the currents. Now this is important. So what gyre does it belong to off the coast of Peru underneath the equator? So right away you should know that's the South Equatorial, but what gyre are we talking about? Make sure you can explain what a gyre is, how many there are. So the agency mentioned in 1C, if they wanted to create another measuring tool, where would they go to? Cite like latitude, like an idea of latitude, longitude. It doesn't need to be both. Really, what I want you to think about here is we're looking at a specific wind pattern. That specific wind pattern is in a certain area. What area is that? Okay, so I need you to think about that one. I won't tell you. I need you to think about, okay, what wind pattern are we looking at? And then go back, okay, where are those wind patterns located? That's where your buoy array, if you're going to make another one, that's where it needs to be. And why was a location selected? It's because that's the wind pattern we need to observe. So it has to fit in that range. And that about covers it.